Hello everyone and welcome to today's lecture. Today we'll be discussing an introduction to graph theory and some of the important operations and ideas contained within. And so to begin with, we'll start by defining a graph and discuss various terminology and different types of graphs that we can have. We'll say that a graph G, we sometimes express it as an ordered pair of two sets. A vertex set and an edge set consist of two sets, a set V, called the vertices, or nodes of the graph, and a set E, called the edges of the graph. Each edge has either one or two vertices associated with it, called its endpoints. And this is why we say that an edge is said to connect its endpoints. I want to remark here that the set of vertices of a graph may be infinite. A graph with an infinite vertex set or an infinite number of edges is called an infinite graph. In comparison, a graph with a finite vertex set and a finite edge set is called a finite graph. We're only going to be considering finite graphs. But it's important that you understand the difference in that many properties that finite graphs have are not necessarily associated with properties of infinite graphs, and vice versa. And I want to make another remark here that the edge set takes different forms with respect to the classification or the type of graph. And so the first type of graph that we'll classify is what's called a simple graph. And for an example of a simple graph, we have the following. Where we'll label the vertices as A, B, C, D, E, F, G. Now, the relative locations of these vertices don't necessarily matter, but what matters in a graph is the interconnectivity, so the edge set, which vertices are connected to where. However, if we're trying to model something in the real world, we can also consider what's called a weighted graph, where either the vertices or the edges have what are called weights associated with them. And this can help us model large distances or costs between vertices. For instance, if we're modeling a computer network, this could be a very simple representative computer network of the United States, where we have the city of San Francisco, Los Angeles, Denver, Chicago, Detroit, Washington, and New York. And this example is given in the book, so there are many different examples that we can use, but the idea here is that the edge set of a simple graph, what characterizes it is that the edges are unordered, and there are no loops, so no edges connected to themselves. So no loops, and the edges are not directed. So unordered pairs are not directed. So for example, the edge set for this graph E, the vertex set, is just A, B, C, D, E, F, G. The edge set is going to be the set of subsets with all of the pairs of elements that are included in as an edge. So in this case, A, B, A, C, B, C, C, D, D, F, D, E, D, G, and lastly FG. These sets are unordered collections of elements. So each one of these subsets represents an edge in the edge set. You have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, it looks like I miss one of the edges. Specifically, I miss the edge EG. There we go. So this is our correct edge set. Now, very often we kind of shorten our notation a little bit, and we just write E as AB, AC, BC, CD, EG, DF, DE, DG, and FG. Where the understanding is that each one of these listings, A, B, A, C, B, C, correspond to a set of unordered pairs of elements. And we have that there's one more classification for a graph to be a simple graph, and that's that there are no multiple edges, or each vertex is connected. Each two vertices are connected by one and only one edge. And this brings to mind then the next classification, which is called a multi-graph. And this is characterized by no loops, and that the edges are still unordered pairs because they're not directed. However, this allows for a slightly more general type of graph, but we allow for the possibility of having multiple edges connecting various vertices in the graph. So for instance, this multigraph would be characterized by having one connection between A and B, one connection between A and C, but now you have two connections between B and C, three connections between C and D, and so on and so forth. This is super useful in applications when we may have more connectivity between certain, say, data centers if we're dealing with computer networks, or you can think of many other different applications, and we'll see many applications a little bit later on. But so this is the edge set for a multigraph, as you might expect, is described in a very similar way, but it's now the edge set is a multi-set, where we allow the elements to have multiplicities. So the edge set in this case is going to be this example. One AC, one AB, two CB, because CB has two edges, three CD, one DE, one EG, two GF, 1 DF, and 2 DG. So we use the notation from the end of the set theory chapter where we learned about multisets. And so the total number of edges is the sum of each one of the cardinalities of each of the edges, and this is a full description of what a multigraph is. The next classification that we have is what's called a pseudograph. And this is what we get when we remove the condition of having no loops. And so this is an example of a pseudograph. Suppose that these data centers between these cities, some of the data centers, maybe the ones in certain areas that are most important, or just have a better upgraded equipment, have self-diagnostic check loops. So the data centers themselves are related under this relation, and maybe New York has more loops than say some of the other cities that have loops, because there's more self-checking going on there. So this is just one good example, kind of extending the example from before. So a pseudograph is something with loops in it, and the only condition is that it doesn't have any ordered pairs in it for its edges. And the edge set for this example is going to be the same multiset as for this multigraph, because we really just copied it over, but we have to add a couple edges, specifically a loop connecting C to itself, a loop connecting D to itself, E to itself, and 2 loops connecting G to itself. So this is a good example of a pseudograph. And so one of the things that I want to point out is that all of these graphs right here are examples of non-directed graphs, because this is the one property they all share in common. And in some sense, non-directed graphs are slightly easier to analyze than directed graphs. However, we want to include directed graphs as well, because they're super important and sometimes even more useful and more realistic than a non-directed graph. So for the first type of directed graph that we have is going to be called a simple diagraph. And for a simple diagraph, we take the main idea from a simple graph and just allow the edges to be directed instead of undirected. So in a simple diagraph, there are no loops allowed. Edges are ordered pairs now, because the order matters, right? Edge AB is different than edge BA. They're not directed, and there are no multiple directed edges. So in between A and B, we can have the edge AB in the graph, the edge BA in the graph, but no more than one directed edge in any given direction or between any 2 vertices. And so this is an example of a simple directed graph. Each of the edges has a corresponding direction, which denotes the ordered pair that is in the graph. And this is an important point here. The edge set E is a set of ordered pairs of vertices from V. Which means that E is a subset of the Cartesian product of the set of vertices with itself, which means that E is an example of a relation on v cross v, and we've already seen this in our diagraph representation of relations, which is very, very cool. So for example, for this graph, the edge set is going to be the set of ordered pairs AC, AB, BC, CB, CD, DC, DE, ED, DF, FD, FG, DG, and EG, and that's all of these edges right here. So the next step up is to consider what's called a directed multigraph, which is similar to the idea from before. And so in the case of a directed multigraph, this is an example of a directed multigraph. We're allowed to have multiple directed edges, and we also allow for the possibility of loops, having loops. So we could potentially have, we'll say, a loop on a number of these vertices. We'll put a loop on G and a loop on F. And it's important to point out that depending on the author, and graph theory is a relatively new subject, relatively speaking, and the idea is that there's different terminology used by different authors. So some authors do not allow for loops, but in the text that we're using for the class, loops are allowed in a directed multigraph, and we have to specify if we're not allowing loops. So the idea then is that for a directed multigraph, like we've just drawn here, the edge set is going to be the following. In general, it's a multi-set of ordered pairs, and the edge set looks like this. It's a multi-set of ordered pairs, so each of these ordered pairs has a certain cardinality, and you see that. You have two AC edges, so two edges from A to C, but only one edge from C to A. And this is a directed multigraph. Right? The next and final main classification is called a mixed graph, which is when we have mixed ordered and unordered edges. And I'll give you an example of a mixed graph. What I'll do is I'll actually take the directed multigraph here and draw a mixed graph that is in some sense equivalent to this directed multigraph. And so this right here, we need to include the loops as well. Almost forgot those. We have a loop here at F and a loop here at G. This is an example of a mixed graph where the edges are ordered or unordered pairs. They can be directed or not directed. But this mixed graph is in some sense equivalent, right, to this directed multigraph right here, because of the idea that if we have two separate ordered edges pointing in both directions, we can in some sense replace that with a single non-directed edge where traversal can go in either direction. Right, so we do that here for these. We have four edges here, which are each directed in the opposite direction, so we can replace that with two non-directed edges. And the edge set here is also going to be similar. It's going to be a collection of sets and ordered pairs, and I should say not just a set, but it will be a multi-set. So the edge set will be a multi-set of ordered or unordered pairs. And this is the edge set for this example that I've drawn right here. And so all of this terminology can sometimes be confusing, so I've included a nice little table right here to help you understand and kind of classify graphs yourself. What I want to emphasize here is that different authors use different notation sometimes, so you have to be very careful, and what it's better to do is kind of specify exactly when you're reading a paper or doing something, trying to show something. You want to specify just each one of these properties that you're allowing or not allowing, instead of try to use a specific terminology. However, these are relatively general terminologies that are accepted by many people, with the main difference being that some authors in a directed multigraph do not allow loops. But the idea here is that each one of these classifications just kind of helps us put things into their place on what a graph is and what different types of graphs there can be, what different properties a graph can have. And for example, we've seen that all edge sets are of a directed graph are relations. So, but a general relation, we can possibly have elements be related to themselves. So a relation R on a set A is a simple directed graph with loops allowed. Right, so if we take a simple directed graph and we add the addition of loops to this simple directed graph, then any relation R on set A is a simple directed graph. Specifically, it's the graph G, the vertex set as A, and the relation itself being the edge set of the graph. And technically, you could also call it a directed multigraph. Where we know in a multigraph the cardinality of each edge can be 0, 1, or any positive integer. So we say that it's a directed multigraph where the cardinality of any edge is either 0 or 1. So this example really kind of, I think, brings home what I mean here is that as long as you're okay with these properties, you'll be able to figure out what your graph classifies as, and what typically if it's in one of these classes, you might want to take with that class or the classification and restrict or add certain properties as you see fit to when you're studying a certain type of graph. So in addition to the structure of a graph, which we talked about before, we can also define the concept of a weighted graph. And this is a graph of any of the previous types in which a number is assigned to each edge. So for example, just using the idea from before, if we take our simple graph, we can give a number to each edge, call it maybe y1, y2, y3, y4, y5, y6, y7, y8, and y9. And this y value could have any number of meanings. If it's, say, a real number, it could denote the distance between the cities, if we're talking about a computer network. It could be the cost of traveling between cities. It could be a very large number of possible applications. And these weights could represent costs, lengths, capacities, depending on what problem you're dealing with. Such problems arise in many contexts. For example, in what are called shortest path problems, such as the traveling salesman problem. And we can also assign vertices weights as well, but typically when you read about a weighted graph, we're talking about an edge-weighted graph. So this is important to know about. In addition, we can talk about a colored graph, or a graph coloring. And this is a special case of graph labeling. It's an assignment of labels traditionally called colors, but they can be any labeling scheme that you want, to elements in a graph, specifically to either the vertices or the edges. If we color the vertices of a graph, we call it a vertex coloring, and if we color the edges of a graph, we call it an edge coloring. So I'll give you a very specific example, and it'll be an important example a little bit later on, and this is called the Peterson Graph. And if we were to just color the Peterson Graph with all of the vertices black, it would be the same shape, right? The same relation, same between the vertices and edges, but this is an example of a colored Peterson graph. And despite what you may think, this is actually a very important concept. The idea is that we have many very important real applied theorems that are important in computer graphics and other areas that are related to how you can cover a graph. Also to many other areas, not just to computer graphics. Specifically, what's called the four-color theorem is one of the big theorems in mathematics that has to do with what are called planar graphs. Which a planar graph is a graph that, simply put, can be embedded into the plane. And what this means more exactly is that the edges of the graph can be drawn in such a way that the edges do not intersect. A very important graph that represents, it's actually what's called a Schlegel diagram of a regular dodecahedron. In 3 dimensions. But this graph is planar. A good example, or non-example, or graph that's not planar is the Peterson graph. No matter how you move around these vertices, you'll never be able to draw this graph in a way where the edges do not intersect each other. So this is not a planar graph. So in terms of describing graphs, what we want to do is make some basic terminology definitions with regards to graph properties. To this end, we'll make the following definitions. Two vertices U and V in an undirected graph are called neighbors or adjacent if U and V are endpoints of an edge. And in an undirected graph, the order of the edge doesn't matter, so we don't have to worry about the order. We also can say that such an edge E is incident with the vertices U and V, and E is said to connect U and V. The set of all vertices that are neighbors of a given vertex V is called the neighborhood of V. And this can be written in set theory directly. The neighborhood of A, if A is a subset of V or a subset of the vertices, the neighborhood of the subset A is said to be the union of all vertices in A and we denote this set as N of V for a given vertex V. If A is a subset of the vertex set, the set of all vertices, we can also define the neighborhood of A to be the union of the neighborhood of all vertices in set A, all of their neighborhoods. And lastly, the degree of a vertex is the number of edges incident to it. And the notation for this is just DEG of V. Note that each one of these concepts we can also extend and generalize for directed graphs as well. But strictly speaking, these are concepts that are solely for undirected graphs. We can generalize each one of these ideas, though, for directed graphs as well, but we have to be very, very careful here. Specifically, for a directed graph, we have to define two separate concepts, the in degree and the out degree of a vertex, which corresponds to the fact that each vertex has a number of edges moving away from it and moving into it. And to that end, we say that when the ordered pair UV is an edge of a directed graph, G is going to be any type of directed graph. U is said to be adjacent to V and V is said to be adjacent from U, because this is an ordered pair now. Order matters. The vertex U is the initial vertex and the vertex V is the terminal vertex, or end vertex. And for a loop, the initial vertex and the terminal vertex are the same. And this gives us the definition then in a diagraph. The in degree of a vertex V is said to be the number of edges with V as their terminal vertex and the out degree of V is said to be the number of edges with V as their initial vertex. And these are denoted as follows. We see that the degree with a minus sign is the in degree, and degree with the plus sign next to it of the is the out degree. So one of the most famous theorems that we have, really helpful as we go along, is if G is an undirected graph with m edges, so the cardinality of the edge set is equal to m, then 2 times m is the sum of all of the vertices, degrees. The sum of all the degrees of all the vertices. And it's important to note that this theorem also applies if multiple loops are present, so to multigraphs, and to pseudographs, so if multiple paths are present or if loops are present. And this can be proven in a very straightforward manner by using induction on M, where M is the size of the edge set. So for notational purposes, we'll call V the vertex set, V1 to Vn, and we'll fix n for a given graph. And then we'll say that E is equal to the set, possibly multi-set of edges, M1 to M. And our base case is going to be when the size of E is equal to 0, or no edges, in which case 2 times the size of E, or 2 times M, is 2 times 0. And because there are no edges in the graph, the sum of the degrees of all the vertices is also going to be 0. If we have one edge in our graph, then 2 times 1 is going to be the sum of the degrees, right? 1 is the number of edges, 2 times 1 is just 2, and the sum of the degrees of all the different values is going to be one of two possible things. Because either we're going to have a loop, so the edge in E is a loop, in which case the degree of one single vertex is 2, so the sum right here is going to be 2 plus 0 plus 0 all the way up to 0, in which case this works. Or if E is not a loop, it's a normal edge, and again 2 times 1 is going to be equal to the degree of two of the vertices in this list of vertices is going to be 1, and the rest is going to be 0. And therefore 1 plus 1 is 2, so this is satisfied for one edge. And you can go through and do as many base cases as you want, but this is enough for us. So the inductive hypothesis is going to be that there exists in M in the natural numbers such that the size of edges in our graph is M, and 2 times M is equal to the sum for all V and V over the degree set, or the degree of every vertex. And then the inductive step. We're going to add one edge to E, and we'll say that E old is the old edge set, we had one edge to E old to get E new edge set. And we'll call the edge specifically little e n. We have that either en is a loop or it is a normal edge. And both of these we can deal with, and I'm going to split this into two parts. And I'll deal with each possibility in turn. If it's a loop, then the degree of one single vertex, vk, or I should say VKO for VKO old increases by 1. So the degree of VK new, which is the same vertex, just compared with the previous step to this new step with En added. The degree of VKN is going to be the degree of VK old plus 1. So the degree of VK increases by 2. Because some vertex has to be connected to this loop, and therefore its degree is gonna increase by 2 because we're adding 2 edges that connect to it. Therefore, if I add up the degrees of the vertices, V and V, for this new En, this is going to be the same thing as the sum of vertices in V degrees without including V equal to VK plus the degree of VK, which I'm going to put new here because we now have 2 new edges that are connected to it. And this is the same thing as the sum over V and V, V not equal to VK, plus the old degree of VK plus 2. And if we change the order of this sum right here, this just becomes the sum of V in VK V in V, V not equal to VK plus the degree of VK old plus 2. And from our inductive step, or from our inductive hypothesis, this entire thing right here is just going to be 2m. So we have 2m plus 2, which is 2 times m plus 1. So we've shown that this holds, the inductive step holds if En is a loop. And the idea here is that if En is a normal edge, this proof is exactly, almost exactly the same. We have that if it is a normal edge, then for two separate vertices, Vi not equal to Vj, the degree of each vertex increases by 1. So you have an increase in the degree of Vi and the increase in the degree of Vj by 1, and thus in a very similar manner to here. I'm not going to go through and show it. It's almost the same step. The sum of the degrees of V end up being directly equal to the original sum of the vertices, which is 2m plus 1 plus 1 for each of the extra degrees in Vi and Vj. This becomes 2 times m plus 1, and our inductive step is done. So this is a very, very important theorem. Because what it's saying is that for any graph, no matter how complicated it is, the sum of the degrees of the graph is even. So it's called the handshaking theorem. Additionally to this, we can prove another general theorem on the number of vertices of odd degree. An undirected graph has an even number of vertices of odd degree. And the proof here is rather straightforward. From the previous theorem, if we'll say that V1 is the subset of vertices of even degree, and V2 will set to be the vertices of odd degree, and from the previous theorem we have that 2m is the sum over all vertices, which can be separated into the sum of the even vertices degree and the odd vertices degree. And the idea here is that because the degree of each one of the even vertices is even, this number is even, and therefore 2m minus this sum right here has to be even. So therefore, the sum of all of the odd vertices must be even, or an even number, and because this sum must be even number, and the degree of v is odd for v in v2, there must be an even number of vertices with odd degree. So the previous theorem is for pseudographs in general, so pseudographs, multigraphs, and graphs, but there's no directed edges in this theorem. We have a very similar theorem for directed edges, and the idea here is that we're going to let G be a directed graph. Then the sum over the vertices in V of the in degree is equal to the sum over V in V of the out degree, which is equal to the size of the edge set, or the number of edges in the graph. This is also very useful, and it's specifically related to diagraphs. So the proof is very, very, very similar to the previous theorem. So I'm going to leave this as an exercise. You should go through and do this using induction. It's a good exercise to go through and do to kind of see that this has to be true. But these are two very, very useful theorems, and what's good about them is that they're valid for all graphs. And the idea is that they're useful in general for proving different things about graphs, graph properties. But we'll continue on and kind of get into some big ideas on how to work with graphs right now. So what we're going to move into is and what we're going to do now is define a very useful tool called the adjacency matrix of any graph that can be defined. And this is going to be a super useful tool for going through and actually proving results and understanding results about a given graph. This is going to be a matrix with a value in its entries of either 0 or a positive integer. That positive integer is going to be the number of edges connecting the vertex is represented by the row of the matrix to the vertex that is represented by the column of the matrix. So this is a very, very similar idea to how we use 0-1 matrices for relations, but it's kind of extending this idea now. So this is the next thing that we're going to talk about.